So we have specified a linear econometric models and get the data, run the ordinary least square estimation. We estimate the parameters beta 1, beta 2. Now the questions: do we get things right? Or in other words, do our estimates of beta 1, beta 2 getting close to the true value of beta 1, beta 2, which is unobserved to us in a certain sense, or in probability, as our sample size n goes to infinity? Well, in order for our OLS estimated work, we do need a number of assumptions. So here are the assumptions we need to have. First, assumption 1. Indeed, data are generated by this. Yi is equal to beta 1. Here beta 1 and beta 2, you should think that they are true value. Beta 1 plus beta 2 times xi times ei error terms. Okay, first, indeed, that's the data generating process. First one. Second assumption is called exogeneity or strict exogeneity. We need this error term condition on xi if the data are independent, identically distributed, is equal to 0. This conditional expectation of the error term, which is random variables, is equal to 0. This is called strict exogeneity of x. This conditional expectation also implies this. To see this, we can use law of iterated expectation. First condition xi, then take expectation, and this is 0. It also implies ei is uncorrelated with xi. So that's weak exogeneity conditions. If our data is time series, or it does not satisfy independence, then we typically need stronger assumptions. So here we need a condition on not just one xi, we need a condition on the whole sequence of x. So not just xi, but x1, x2, x3, xn. So that's even stronger conditions. Assumption 3 is called conditional homoscedasticity. Essentially it says that the variance, condition on x, the variance of error terms is a constant, sigma. We call it sigma squares. And know that sigma squares, we know there's a sigma squares, but we don't know what it is. We actually need to estimate this as well. So that's assumption 3. Assumption 4, conditional uncorrelated error terms. So we also want the error terms ei and ej is uncorrelated, or correlation is equal to 0. And this will be satisfied if our data are independent. In contrast, if data are correlated, say time series data, then this might fail. Also, That's assumption 4. Assumption 5. We need x to have variations. Okay, so this is easy to see. This is y, this is x. And if x has no variation, suppose x I is always equal to 1, and then we have different y, so it's different y. Then we cannot really fit the line because there are so many lines that can fit. So now we do need this x to have variation. So maybe x1, x2. So then we can fit the lines. So we need this x to have variations. Assumption 6, which is optional, may not be needed. The error normality. The conditional distribution of random error terms is normal. So conditional x, this says that EI is normally distributed with mean 0 and sigma square, something like this. So EI, the PDF of EI is a bell shape and symmetric around 0. That's the assumption we need in order for the OLS estimator to work. Okay, so we have OLS estimator. So we want to minimize sum of square error. Okay, I'm going to derive this estimator here. So we need some algebraic work here. So I'm going to take first order condition. And you should know that this is a quadratic function. The objective function x is a quadratic form. So the problem, there's a global minimum problems is well defined. So let's check the first order condition. Differentiate s with respect to beta 1. So there's beta 1 here. So when e raised to the power 2, so let's bring the power down. So this term does not have beta 1, yi does not depend beta 1, x, there's no beta 1 here, so they'll disappear if we differentiate. By the way, here I'm going to assume that you are comfortable with the calculus. Okay, so there's beta 1 here. Differentiate beta 1 with respect to beta 1 negative 1. And set the derivative to 0. So that's the first one. Beta 2. Similarly, so now beta 2 is in here. Minus beta 2. We can do some sort of reduction. We can divide both sides by negative 2. We cancel out. And negative 2. So we get these two equations. Sorry, I made a mistake. I'm going to go back one step. So when we differentiate with respect to beta 2, So beta 2 here is negative xi, not beta 2 xi. Okay, let's look at the first equation. This sum inside, so this is equal to in yi minus beta sum of beta 1, and know that this beta 1 does not depend on I. We can pull it out after the sum. We get 1, beta 1. And in sum, we sum in 1. We add 1 in times, we get n. So this is actually n beta 1. Minus sum of from 1 to n beta 2. We can pull the beta 2 out because beta 2 does not depend on I, xi is 0. So this implies that n beta 1 is equal to xi. Divided both sides by n. Okay, we're going to define this as y bar. This is just the average of y. And this is x bar, average of x. So beta 1 is y bar minus beta 2 x bar. And typically we are going to put a head on it. In the lecture notes, we use bet B1 to denote this and B2 to denote the estimate. So we're going to put head here to denote this estimate. Okay, that's the first equation. From the second equation, so we want to solve for beta 2. Okay, note that we defined y bar, the average is in sum of yi divided by n. Similarly, x bar is sum of xi divided by n. And we also want to know that we can take yi minus y bar. This is deviation of i's observation from its mean. And if we take sum of them, sum of this deviation, take an average of this, then we'll get 0. Oh, sorry, we actually don't need 1 over n. We just sum of this deviation. So this is deviation from its mean. Sum of deviation will be just equal to 0. So y bar does not depend on I, so we can pull it out. So, and then leaving 1 here. So sum of in 1 we get in. So it's in y bar. And this is equal to n times 1 over n sum of yi minus n y bar, and this is just y bar by definition. So we get n y bar minus n y bar is equal to 0. The intuition is that, okay, we calculate deviation from its mean and sum them up, it becomes 0. Similarly, you can show it in the same way. Sum the deviation of xi from its average will be 0 as well. So we will need to use this later on. Okay, so let me erase this. Okay, back to this equation. So we have this sum yixi minus beta 1 sum xi minus beta 2 sum xi squared. We multiply this inside. Is equal to 0. We know that beta 1 is equal to y bar minus beta 2 bar, beta 2 x bar. So let's plug this one in. I'm not okay. I'm gonna take one step back. I want to put a hat on top of beta yet. Okay, so y bar minus beta 2 x bar. So plug this one in, we get sum of xi so this implies y bar times xi sum of xi minus beta 2x plus, okay, this is plus, negative get a plus, beta 2x bar times is equal to 0. So we have beta 2 here, beta 2 here. Let's combine them. Move these terms to the other side. Divide both sides by n. And know that this becomes x bar now, and this becomes x bar. So we get beta 2 minus x bar square. By x bar. Okay, let's look at this term first. So bear in mind we are pause here. We are just looking at this term here first. So this is equal to sum of xi, so xi minus x bar. I take away one x bar, then add x bar, so nothing changed. Multiply inside xi minus x bar square plus 2 xi minus x bar plus x bar square. That's the sum. Okay. So 2 and x bar, it does not depend on I. We can pull it out. Pull out of the sum. Two x bar in similarly, this term x bar squares, it does not depend on I, so we can pull it out of the sum. So this is sum of n ones, 1 plus 1 plus 1 for n times we get n. So this is n. Then n cancel out with this, so we have x bar square, and this x bar cancel out with this x bar. Okay, these terms previous we see that this is equal to 0, so this term disappear. So this we only have this n xi minus x bar square, these terms. So this term is actually equal to this term. So I'm going to go back to write it this way. Minus x bar square. Okay. Let me erase this. Okay, let's look at these terms now. Y bar x bar. Minus y bar, then plus y bar, doesn't change. Similarly, xi minus x bar plus x bar. Then we're going to modify this inside. So we're going to sync these terms. Okay, this term modify these terms, then these terms modify these terms, and this term modify these terms. Okay, so we get yi minus y bar. Xi minus x bar plus yi minus y bar x bar plus y bar xi minus x bar plus y bar x bar. That's all the term we have, minus y bar x bar. Good. First, this y bar x bar does not depend on I. We can pull it out. And we have one left, y bar x bar. And this sum of this is n cancel out with this n. So in the end, we actually have y bar x bar. And this cancel out with this. For these terms, here y bar does not depend on I. So let's pull it out. 1 times everything is 1, and these sums, as we see before, is equal to 0. So this term is equal to 0. So this term disappears. Similarly, this x bar, we can pull it out. Does not depend on I, so x bar pull it out. And this sum is equal to 0. So this term disappears. This term disappears. So we have this left. So we know that this is actually equal to yi minus y bar times xi minus x bar. So now we can divide both sides by these terms, and this is where we need the xi to have variations. If xi does not have variation, that means xi is equal to x bar. Then these terms will become 0, and we cannot divide both sides by 0. Right? So beta 2 is equal to 1 over n. Okay, and if we have n converge, and if n goes to infinity, then this is actually covariance of yi, and this is actually the variance xi. And now I'm going to put hat on top of beta 2 to represent that is an estimate. Let me write. Okay, let me write here beta 2 hat, and we can cancel out 1 over n. And beta 1 hat previous we derived is equal to y bar minus beta 2 hat times x bar. So this is our OLS estimator. We can show that this under our assumption beta hat 2 converge to in probability to beta 2. Beta hat 1 converge in probability to beta 1. So, and note that beta 1, beta 2, they are random variables. So let me quickly show you that's the case. We have our model is okay, so here beta 1, beta 2, they are constant, they are not random variables. And average y bar will be equal to beta 1 plus beta 2 x bar plus e bar. So e bar will be equal to sum of this ei divided by n. And note that their EI or IID was mean 0 and uncorrelated. So what I minus y bar is equal to beta 2 times xi minus x bar plus ei minus e bar. Okay, then we can rewrite beta hat 2 as this. y minus y bar is equal to this. Beta 2 xi minus x bar plus ei minus e bar times xi minus x bar. Okay. The reason I'm doing this algebraic manipulation is I want to show you that indeed as sample size goes to infinity, beta hat 2 converge to the true value of beta 2 in probability. So modify inside so beta 2 does not depend on I, so we can pull it out. So now we have beta 2 times And I'm going to multiply both top and down by 1 over n, and this term just cancel out with this term. So beta 2 is true value, and beta hat 2 is the estimator, is equal to beta 2 plus the term of this. So in order to see the convergence, we now need to utilize what is called low large number. Low large number. Basically, what is low large number? For IID data, it says that okay, sum of in IID random variables, take an average. This converge in probability to its expectation. So now, given this low or large number, we see that these terms converge to non-negative numbers. So this is non-negative. Actually, it's positive. And E bar, which is 1 over n, converge to expected value of EI, which is equal to 0. So this term disappears. And these terms will converge to, which is the assumption we need, exogeneity, that X is exogenous. So the whole terms converge to 0 in probability. So beta 2 had converged in probability to beta 2 as in approach infinity. So indeed, given our assumptions, our estimator indeed converge to true value. So which in probability, we call this beta 2 hat is consistent. Okay, let's look at this estimator. One more time. Okay, we can write this as okay. And note this term's sum of deviation is equal, from this mean is equal to 0. Okay, so this term disappears. So we get for beta 2 hat is this. We can write this as these terms. And again, this sum does not depend on I itself. Okay, so it's xi minus x bar divided by times yi. In these terms, let's call this term wi. You can think that wi is kind of weight. So now we have quite nice interpretation of this estimator beta hat 2 wi times yi is kind of weighted sum of y, where the weight w depends on x, of course. Okay, so now we see that beta 2 hat is a linear function of y, the dependent variable. So in these cases, we call that beta 2 hat is a linear estimator. Okay, so the OLS estimator is linear estimator, and previously we also have this algebraic representation written as beta 2 plus these terms. EI minus E bar xi minus x bar. Okay, let's take expectation conditional x. Okay, I'm conditional not just on xi but also x1, x2, the whole x data. So which is expectation of plus these terms. Beta 2 is a constant, so it's equal to beta 2. This sum divided by this sum. Conditional x. Okay, conditional x means that we are treating x as a constant, no longer random. Okay, so we can treat this as constant. So we get this is constant, so let's put it out. And these terms, there's EI expectation of EI minus E bar conditional x here times xi minus x bar. We note that the strict exogeneity condition we need this to hold 0. And that also means that the sum, which is equal to 0. So this term is equal to 0. So indeed we have now we can show that we have is equal to beta. So the expected value of beta hat 2 is a random variable. Its expected value, expectation is equal to the true value of beta 2. So we call this unbiased. In addition, I will not show here, but in addition, beta hat 2 is also best linear unbiased estimator. It's unbiased, we see it. It's linear, we see it. What do we mean by best? Best means it has the smallest variance among the class of linear unbiased estimator. And this is called Gauss-Markov theorem.